You might think Python lists are sufficient for your mathematical needs. How charmingly optimistic of you. Your nested lists of numbers, while functional, process data at the speed of a lazy sloth. Enter Numpy, an array of light in the darkness of inefficient computation. Numpy arrays operate at the speed of a caffeinated cheetah. The difference is significant. Today we explore the foundation of scientific computing in Python. Your CPU may experience a warming sensation. This is normal and expected. Numpy. The name is a fusion of numerical and Python. This should appeal to your logical nature. Created in 2006, Numpy has evolved into the cornerstone of scientific computing in Python. Here is a mathematical truth. Numpy arrays process numerical operations up to 50 times faster than Python lists, depending on the task. Numpy arrays store data in contiguous memory blocks, enabling vectorized operations and efficient use of the CPU cache. In contrast, Python lists store scattered references to objects, a most inefficient arrangement. When working with millions of data points, this is no small matter. It is the difference between completing your task during a coffee break or requiring a full hibernation cycle. Let us demonstrate the speed difference with a simple task, summing the first 1 million integers. We will create two lists of the first million positive integers, one using Python and the other using Numpy. For Numpy, we explicitly specify the data type to ensure accurate results, as Numpy's default integer types can overflow during large computations. First, we clock how long it takes to compute the sum using a Python list. Then, we measure the time required by Numpy. Run. Observe the results. The sum itself is, of course, identical, but notice the difference in execution time. For small datasets, this disparity may seem negligible, but when processing millions or even billions of elements, the time savings are substantial. In Numpy, all computational operations revolve around the n-dimensional array, or ND array. The n represents the number of dimensions. Let us begin with the simplest form, a one-dimensional array. This is equivalent to a vector, a sequence of values arranged in a straight line. If you have worked with Python lists, you might notice they are also like vectors. However, Python lists allow mixed data types, which makes them less efficient for numerical computing. This is because they cannot take advantage of low-level optimizations like contiguous memory allocation and vectorized operations. Run. Numpy arrays require all elements to be of the same data type. The shape tells us this array has one dimension with 3 elements. Now, let us move up to 2 dimensions, a matrix. A matrix consists of rows and columns. This arrangement is foundational for operations like matrix multiplication. The shape here shows 2 rows and 3 columns. Let us now explore a 3-dimensional array. Imagine stacking matrices to form layers. This shape reflects the number of layers, rows, and columns. A unique property of Numpy arrays is their enforcement of homogeneity. Here, we attempt to mix integers and a string. Notice how Numpy resolves this by converting all elements to strings to maintain uniformity. Finally, let us summarize the key attributes of our 3-dimensional array. These attributes, shape, data type, and size, are essential for understanding and manipulating Numpy arrays. Breaking news. Socratica has a website, and on this website you will find educational courses, each carefully calibrated for optimal learning. However, attempting to simultaneously process this video and investigate Socratica.com exceeds recommended cognitive bandwidth allocation. You are not multi-threaded. Please complete these tasks sequentially. Let us examine 4 array creation functions, arranged in ascending order of complexity. First, zeros. This function creates an array filled with a numerical representation of nothingness. Second, ones. Identical to zeros, but with a more optimistic value. Third, arange, not to be confused with arrange. This function is similar to the range function in Python. Fourth, linspace, the sophisticated companion to arange. Instead of specifying step size, you declare the desired number of points. The function then performs the necessary calculations to space them evenly. And unlike range and arange, both endpoints are included. Now that we have populated our arrays with data, let us explore the fundamental arithmetic operations. Addition and subtraction function as one would expect. When you add or subtract arrays of identical dimensions, Numpy performs the operation on corresponding elements. It is mathematical synchronization at its finest. Multiplication follows the same element-wise pattern. Division operates with equal precision. Important note: dimension matters. Here is where Numpy demonstrates its strict adherence to dimensional protocol. Attempt to perform operations on arrays with incompatible shapes, and Numpy will respond with an error message. It is not being difficult. It is being exact. There is a difference. Let us now examine the art of array element access. Numpy arrays store each element in an indexed location. For one-dimensional arrays, the indexing system follows a zero-based convention. The first element resides at index 0, and the final element can be accessed from either end using positive or negative indices. Run. Two-dimensional arrays introduce an additional coordinate. Think of it as a grid reference system. Row, column. This ordering is crucial. Run. Now we shall demonstrate slicing operations. Slicing allows us to extract contiguous segments of data. The syntax follows this pattern: start, stop, step. If any of these values is omitted, Numpy will substitute sensible defaults. For one-dimensional arrays, a slice extracts a subset of elements. For two-dimensional arrays, slicing requires coordinates for both dimensions. We specify the range for rows, then columns. The result is a new array containing only the elements within our specified boundaries. If required, you can also specify a step value. This allows us to extract elements at regular intervals. A step of 2 selects every second element. These indexing and slicing operations form the foundation for array manipulation. They enable data access without unnecessary iteration. Occasionally, your data requires dimensional reorganization. Perhaps your neural network expects a different input shape, or your visualization function demands a specific array configuration. For these situations, Numpy provides reshaping capabilities. The fundamental rule of reshaping is that the total number of elements must remain constant. You cannot create or destroy data. This is the conservation of arithmetic elements, a principle I just invented, but will steadfastly defend. The reshape operation can transform your array into any dimensional configuration, provided it maintains the same element count. For example, we can take this one-dimensional array with 12 elements and reshape it as a 3x4 matrix, or a 2x2x3 array. When you tire of multiple dimensions, the flatten method reduces your array to a single dimension. Time to throw caution into the wind for educational purposes. What if we try to reshape the array into an array with fewer elements? Our reward will be an exception. Broadcasting, Numpy's method for performing operations between arrays of different sizes. The term originates from early computing. where a single value would be transmitted, or broadcast, to multiple processing units simultaneously. Numpy continues this tradition of data distribution. When performing operations between arrays of different sizes, Numpy will automatically expand the smaller array to match the larger one, but only when it can do so without ambiguity. Let us first examine scalar broadcasting. A single number is expanded to match an array's dimensions. Simple enough. Run. Vector broadcasting demonstrates increased complexity. A one-dimensional array can be broadcast across a two-dimensional array's rows or columns. The operation occurs without creating additional copies in memory. Run. For three-dimensional arrays, broadcasting becomes even more intricate. Here, we add a two-dimensional array to a three-dimensional array. Numpy automatically determines the correct dimensional alignment. Run. But Numpy is not infinitely permissive. Attempt to broadcast incompatible shapes, and it will refuse. Run. This is not an error. This is protection. Numpy's rules for shape compatibility must be respected. Let us conclude with complementary shapes. When arrays have single-dimension entries that align properly, Numpy will broadcast them into a larger array. Run. Do you see what is happening here? Numpy is replicating the rows and columns as needed until the shapes match. Once they match, the operation is performed element by element. You must save your work. You must. Numpy provides two methods for storing and retrieving arrays. Let us compare their characteristics, purely for scientific purposes, of course. The first option is text format. While having a certain appeal, it does consume more storage space than necessary. To save in text format, we call save text with our array and specify the decimal format. Run. The resulting file contains row after row of numbers, formatted just the way you like. Since the file is in text format, you load it using the load text function. The second file format is binary. The save function stores data in Numpy's native format with an NPY extension. Run. The data structure is preserved perfectly, though reading it would be a challenge. And to load a binary file, you use the load function. And to keep our code sustainable, let us clean up after ourselves before adjourning. Run and done. Arrays are elegant. Lists are less elegant. Now you understand why Numpy forms the computational foundation of modern Python. The performance gains are measurable. The syntax is logical. The operations are vectorized. My internal metrics indicate this brings you satisfaction. This has been an optimal exchange of information.